Hello, I'm Brent Gary from NASA, and I will be talking about lava tubes on Earth and the Moon. Lava tubes are tunnels or conduits created during volcanic eruptions that serve as underground pathways for lava to travel tens of kilometers from the vent, protected and insulated by overlying crust, which keeps the lava from cooling too fast. After the eruption stops, the lava drains out, leaving an empty lava cave that can be explored for clues to the eruption. The formation of active lava tubes has been observed and documented in the field. Two common ways they form are by the roofing over of a lava channel or the coalescence of lobes in a bohoi flow. Since most lava tubes were not observed while active, textures in the flow structures on the interior of lava tube caves provide a little insight into the eruption. The existence of lava tubes on the Moon has long been discussed by planetary geologists for their science and potential as shelters for astronauts. One of the best ways to anticipate what we might find inside lunar lava tubes is to explore lava tubes right here on Earth. The driving questions for this research are: what instruments are optimal for lava tube exploration, and what might we find on the interior of lunar lava tubes? In this talk, I will discuss results from a LiDAR survey of Lava River Cave and make a few comparisons with pits in volcanic terrains on the Moon. Discovered in 1915, Lava River Cave is located approximately 24 kilometers northwest of Flagstaff, Arizona in the Coconino National Forest. This lava tube is open to the public and is managed by the U.S. Forest Service. Geologically, the lava tube is part of the San Francisco volcanic field, which has more than 600 volcanoes, most of which are basaltic cinder cones. Volcanic activity in the San Francisco volcanic field began approximately 6 million years ago, but Lava River Cave formed approximately 650,000 to 700,000 years ago, according to information on the U.S. Forest Service website. In June 2019, I completed a LiDAR survey of the lava tube over the course of 4 days. I spent a total of 24 hours within the lava tube to collect the LiDAR data. I used a Regal VZ400 terrestrial laser scanner with a Nikon DSLR camera attached to the top. This scanner has a range of 400 meters, and individual scans take 6 to 12 minutes, depending on the selected resolution. The scanner is mounted to a tripod and is moved and set up again and again at new positions along the length of the tube. 77 scans were completed, 7 on the surface and 70 within the lava tube. The 7 surface scans provided an initial georeferenced point cloud. Interior scans were then manually added one by defining a set of control points with the main point cloud. The final point cloud is 3.2 billion points. So why complete a LiDAR survey of Lava River Cave? The cave system has already been mapped in detail in 2 dimensions. However, 2-dimensional maps are static, and it's difficult to grasp a full sense of the morphology of the lava tube. LiDAR data provides a 3D model and complements the 2D map that gives a full sense of the tube morphology at the meter scale and preserves flow textures and structures at the centimeter scale, all within the same dataset. The point cloud of the lava tube can be viewed as reflectance, height, and true color. Measurements can be taken anywhere in the tube, including hard-to-reach spots, and this includes cross-sectional data as well as the relationships between the tube and the surface. Point data can be filtered to show only the floor and the ceiling, and surface comparisons can be made between a mesh of the ceiling and floor to create a map that shows the changes of ceiling height along the tube segment. These are just a few examples of how LiDAR data of a lava tube can be analyzed. Lava River Cave has a single entrance, a shallow pit at the downflow end of the tube segment with an opening that barely fits 1 or 2 people at a time. There is a steep scramble down some rubble to get to the tube. It appears the entrance is where overlying material has collapsed, allowing just enough space to reach the lava tube. Measurements between the surface and the ceiling of the lava tube show the tube is approximately 14 meters below the surface. The tube segment is over a kilometer long at 1,164 meters, but probably only represents a partial segment of the original tube system. This lava tube has a single primary conduit with one section where it bifurcates and rejoins. The tube makes some sharp bends, including a nearly 90-degree turn at one point. No side tubes or branches were observed. The ceiling of the tube undulates with heights up to 9 meters and lower areas where the ceiling and floor leave less than 1 meter of crawl space. LiDAR helps to visualize how the ceiling at the donut ring is high at the bifurcation point and where it becomes a single tube structure again, but lower along the ring segments. Looking at the change in elevation of the floor of the tube, the floor of the upflow or distal half of the tube remains at the same elevation until it reaches the bifurcation point. From there, the elevation of the floor then drops a total of 10 meters until the end of the tube segment. Flow textures along the floor of the lava tube is like popcorn, and it has some smooth areas as well as some hoi ropes preserved. The walls are also relatively smooth with interior lining or a rind present similar to the layers of onions. Debris from the collapse of this lining along the walls and ceiling are present along the entire length of the tube. The sinuosity of Lava River Cave is 1.24, which is comparable to Hadley Rill at the Apollo 15 landing site, which has a sinuosity of 1.27, as published in Hurwitz and others 2013. So let's journey to the moon. In 2009, JAXA's Selene terrain camera captured images of a pit with vertical walls in Mari's Hills that was interpreted as a possible skylight in a lava tube, as it was located in what is apparently a roofed-over section of a sinuous rill. Follow-on global surveys with LRO's narrow-angle camera began to discover additional pits in the Lunar Maria as well as impact melt deposits. Over the last decade, 17 pits have been discovered in the Lunar Maria in previous studies by other researchers. Recently, I discovered a new pit in Marius Hills region that I will discuss here for the first time and brings the total up to 18 pits in the Lunar Maria. Lunar pits have two common morphologies. The first type are open pits with near vertical walls, possible overhangs, and high depth to diameter ratios. The second type are shallow, closed pits with sloped or bowl-shaped floors and a low depth to diameter ratio. Marius Pit 1 is a classic example of the first type of pit, with near vertical walls that have layers exposed. This pit is 40 meters deep and has roughly circular shape at 49 by 58 meters wide. Marius Pit 2 is an example of the second type of pit with a ramped or sloped floor and a vertical or steep walls on the opposite side, but with no apparent overhangs. This pit is 95 by 70 meters wide. Marius Pit 3 is a newly discovered pit and marks the 18th pit found within the Lunar Maria. Located approximately 33 kilometers south of Marius Pit 1 near Galilei M crater, this pit is found within a nondescript volcanic terrain. The pit is oval-shaped at 90 meters long and by 55 centimeters wide. The floor is sloped from east towards the west, and the depth is approximately 26 meters on the western side of the pit, based on shadow measurements on NAC images. Lava River Cave Pit and Marius 3 Pit have similar geologic settings. Both are the only pit in the area with shallow, bowl-shaped or sloped floors, within a relatively featureless volcanic terrain surrounded by volcanic cones, but with no well-constrained source vents. For Lava River Cave, the flow direction of the tube is east to west, so cinder cones that are 4 to 8 kilometers to the northeast and east are the best possible sources for this lava tube. For Marius Pit 3, the local slope in the area is also from east to west. Lava flows where this pit has formed are probably sourced from cones 17 kilometers to the south-southeast, or flows related to a linear rill 6 kilometers to the east. The formation of Marius Pit 3, as well as other pits, could be due to a variety of geologic processes. Some could be tectonic in origin, or inflation rise pits, where lava flow raised up around a pre-existing topographic high. Lunar pits may also be related to lava tube structures. Geophysical surveys around Marius Pit 1 by the Selene and Grail missions suggest a link between the pit and a long void space or cave structure. An idea presented by Yokota and others in 2018 suggests that the shallow pits could be voids filled in by debris from impacts or collapse of vertical walls over time. An alternative to this last idea is based on observations of Lava River Cave. Here the tube is deep beneath the surface, so the collapse of the overlying material into the lava tube void space still creates a pit, even if it did not directly expose the tube segment like a skylight. This process of collapse into a deep-seated void space or tube might be a common mode of formation for pits with the sloped or bowl-shaped floors in the Lunar Maria. Some of the shallow pits on the Moon could also have formed where the tube is only a few meters below the surface, but there is blockage or the tube pinches out. This is observed at the entrance and distal end of Indian Tunnel, another lava tube that we surveyed for the Finesse project at Craters of the Moon in Idaho. The first and last pit are shallow, asymmetric, bowl-shaped, with limited access to the tube. This is in contrast to the other pits that open directly into the deeper sections of the main tube, creating skylights. Pits in the lunar maria may have formed by a variety of geologic processes. No matter how they form, their link to the lunar subsurface is intriguing, and exploration of these features should continue to be a high priority for future surface missions on the Moon. LiDAR is an optimal instrument to explore both terrestrial lava tubes and lunar pits. This type of instrument can quickly acquire topographic data and work in low light or shadowed regions, which makes LiDAR an ideal instrument for planetary exploration of subsurface features. LiDAR is best suited for a rover mission or a mobile platform on the Moon, and the data can inform both science and mission operations. Until then, exploration of terrestrial lava tubes will provide insight into the types of relationships between the surface and subsurface of pits formed above lava tubes, and also help anticipate what could be discovered within a lunar lava tube cave if a mission is ever able to explore inside one of them. This research was funded by the Survey Finesse team, PI Dr. Jennifer Heldman of NASA Ames Research Center, and the LiDAR survey was conducted with permission from the Supervisor's Office of the Coconino National Forest. On a final note, I just want to congratulate you, Jim, on this award, the culmination of a fantastic career. Thank you so much for being my mentor, as well as my colleague and friend, and I just wish you well in your retirement. Thank you so much for the many adventures. I've learned a lot, and I'll just try to do my best to pay it forward.